Okay, so welcome to this morning's session, which is talking to you all about system dynamics. Now, system dynamics is a modeling method that allows us to unpick the structure of a system. So in the previous last week, when we looked at discrete event simulation, we talked about how that was all about essentially queuing problems, that we're looking at people or things flowing through discrete sequential processes and the queues that build because they're waiting for resources. Okay, with system dynamics, it's slightly different. So system dynamics is essentially all about the structure of the system itself. What are the components within the system and the way in which they relate to each other. And the fundamental principle of system dynamics is that structure determines behavior. So it tends to be where you're seeing where the actual structure of the system, the way the system is set up and the way things flow between various elements of a system and interrelate, those are the things of interest in system dynamics. Now that can seem a bit odd, but we're delighted this morning that we've got Dave Spencer, who's going to be talking to us later about a fantastic project that he's done using system dynamics earlier in the year, looking at planning for COVID locally. So that will hopefully give you a really nice idea of the sort of thing that you can do with system dynamics modeling. We're going to start off talking about system dynamics in terms of qualitative system dynamics. So there's two kind of branches of system dynamics. There's qualitative system dynamics, which is what we're going to talk about now, and quantitative, where essentially we plug in numbers and get some results that make some sort of prediction. And those predictions are a little bit different from the sort of thing that you would be used to in terms of discrete event simulation or other modeling methods. And we will come on to quantitative system dynamics. We'll touch on it a little bit later this morning. And then in the next session for this module in a few weeks' time, where we look at Insight Maker in more depth, you'll actually get some practice on building a quantitative system dynamics model where you actually build a model that has numbers in it. But qualitative system dynamics is essentially the way in which all system dynamics models are underpinned. And essentially describes the configuration of a system, and it's in that configuration of the system that interesting things can emerge, and from that those interesting things we can draw insights. So qualitative SD is all about basically creating a map of influences and their directionality, and I'll explain a bit more about that at the moment. And essentially what you typically do is to create a causal loop diagram, which some of you may have come across before, but basically the idea is you look for things called feedback loops, and I'll explain a bit more about those in the moment. But you're looking for certain configurations that tell you something about the way in which your system is set up and how that will influence the way in which your system is working. And then once you've done that, you can then use that map and those identified feedback loops to draw insight from the map and from the loops to better understand how your system is behaving and why it's behaving in a certain way, so you can potentially think about how you might resolve a problem. Now that all sounds very unsubstantial. So let's have a look at some examples. So let's think about some example influences. So let's look at the top here. So here we've got a factor called the number of people accessing GP services. And here we've indicated that will influence the waiting time to see a GP. So, whenever we build a causal loop diagram, we indicate two things. We indicate both the direction of the influence. So in this case, the number of people accessing GP services affects the waiting time to see a GP, and also the polarity of the influence. And what we mean by the polarity is, as this thing over here increases, the thing that's influencing this thing, does this thing also increase or does it decrease? So that i.e., do they go in the same direction or do they go in opposite directions? If they go in the same direction, we indicate it with a plus. So in this case, as more people access GP services, we would see an increased waiting time to see a GP. So they're both going up. Okay, so that's a positive polarity. You may also have examples though where they go in opposite directions. So here's an example where we have the number of people who are admitted to hospital influences the number of beds that are available in the hospital. But of course, in this case, the more people that get admitted to hospital, the fewer beds are available in that hospital. So as this thing increases, this thing decreases. So they go in separate directions, and we mark that with a negative polarity. So positive polarity, they both go in the same direction. Negative polarity, they go in opposite directions. And we mark that with a plus or minus at the end of the arrow. So at the point at which it's going into the thing it's influencing. Now, where it gets interesting is as we start to build up causal loop diagrams, we tend to find that loops emerge, known as feedback loops. And feedback loops are very interesting to us because they indicate certain things about our system. So one of the types of feedback loop that you will see is a reinforcing loop. Colloquially, you might refer to it as a vicious or even maybe a virtuous circle, depending on what the effect is. But essentially, this is kind of your snowballing effect type thing. So let's look at an example here. So we've got the number of people accessing GP services, and that influences the waiting time to see a GP, which in turn influences the number of sick people in the community, which in turn will influence the number of people accessing GP services. So we've got a feedback loop here. And if we look at the polarity of each of these influences, then we can see that as the number of people accessing GP services increases, then we would expect the waiting time to see a GP to increase. They both go in the same direction. That's a positive polarity. As the waiting time to see a GP increases, the number of sick people in the community will increase. So they both go in the same direction. Again, a positive polarity. And as the number of sick people in the community increases, then the number of people accessing GP services increases. So again, a positive polarity. So they're all going in the same direction. And that causes a reinforcing loop. And if we think about that, that makes sense. If you've got more and more people accessing GP services, then your waiting time is going to go up. And that can lead to more sick people in the community, which means more people need to access a GP service, and you've got that snowballing effect. And that's what we mean by a reinforcing loop. Now, it may be that they all have exactly the same polarity within a reinforcing loop, but it may not be. And in fact, what you're actually looking for in order to identify a reinforcing loop is a loop that has an even number or zero of minus polarities. Okay, so if it's got no negative polarities, then it's a reinforcing loop. Or if it's got an even number of them, then it's a reinforcing loop. Now, the way you identify this is by counting the number of pluses and minuses, essentially. But if you think through what you're actually saying, there's a little tip that you can use to double check that you're getting to the right, identifying as the right kind of loop. So if it's a reinforcing loop, every time you go around the loop, you should reach the same conclusion. So here, if I start with number of people accessing GP services, if that increases, waiting time to see a GP increases. If waiting time to see a GP increases, number of sick people in the community increases. If number of sick people in the community increases, number of people accessing GP services increases. And that's what I said at the very start, number of people accessing GP services increases. So I've said the same thing, I've come back to the same thing that I said at the start. If we look, sorry, just before we move on, where reinforcing loops get particularly interesting, or indeed any feedback loop, is where they spill out into other things. So here, clearly, there's a potential issue. If that was in our system, we may think, okay, there's a potential issue here because the worse the waiting times get, actually, we're creating a rod for our own back, because it's going to mean that more people are going to need to access our services, which is only going to exacerbate the problem and make the waiting time worse. But of course, it may not just be in this particular this bit of the system. And it may be that it spills out into other things. So the number of sick people in the community may also influence the number of people attending A&E. So as that increases, the number of people attending A&E increases, which means as this snowballs over here in this loop, this gets worse and worse as well. Now that's a fairly obvious example. of a loop that we all be fairly familiar with. This idea that, you know, if people are struggling to see a GP, essentially that they may well then turn up on A&E, and that causes strain over here. But by putting this into a causal loop diagram, we expose that particular relationship. So we're seeing something about the structure of the system that is telling us information about our particular problem. So here it's indicating this particular reinforcing loop needs sorting, because not only is it causing a problem here, it's also causing a problem for A&E as well. On the other side of things, you can also get things called balancing loops. And now in a balancing loop, essentially things balance themselves out. And a reinforcing loop is kind of a snowball effect. Things get worse and worse and worse and worse. Or, of course, if it's a virtuous circle, maybe that they're getting better and better and better. You can have a positive reinforcing loop too. But in a balancing loop, things sort of balance themselves out. So let's think about this as an example. So if we've got the number of people who are admitted to hospital, that will influence the number of beds that are available in the hospital. And that in turn will influence the hospital's capacity to admit patients. And that in turn will influence the number of people who are admitted to hospital. Now that's a loop, because everything's sort of loops back on itself. But there's a slightly different nature to this loop, because we see a balancing effect. So here, we think the number of people admitted to hospital, as that increases, as more people are admitted to hospital, the number of beds available in the hospital decreases. Okay, so that's a negative polarity. As that one goes up, this one goes down. As the number of beds available in the hospital decreases, the capacity to admit patients also decreases. If you've got fewer beds, you've got less capacity to admit new patients. So they go in the same direction. We indicate that with a plus. As that goes down, that also goes down. Then as the capacity to admit patients decreases, the number of people admitted to hospital also decreases, because you've got less capacity. Now, if we think about that, that of course is a balancing loop, because essentially it's balancing itself out. You're saying, well, as more and more people come into hospital, we've got fewer beds, so we can admit fewer people, and therefore fewer people get admitted to hospital. That of course has to be the case, because otherwise, you know, hospitals don't continue admitting people beyond the capacity that they have exponentially until, you know, the hospital is just overrun with people and no beds. So it balances itself out. If the hospital doesn't have capacity, then you're getting fewer people admitted to the hospital, which means that your strain over here is gradually relieving. That can only be the case. Now, in this case, we identify a balancing loop because it's got an odd number of minus signs. In this case, it's got 1. So we've got one influence where the thing influencing is going in an opposite direction to the thing being influenced. In this case, the number of people admitted to hospitals, that increases, the number of beds available decreases. So we've got 1. And if it's any odd number of minus signs, that will be a balancing loop. And you can test this, just as we did before, by talking through the loop and seeing if you come to a contradictory conclusion once you get around the loop. So as I said, if we start by saying, as number of people admitted to hospital increases, number of beds available decreases. As beds available decreases, capacity to admit patients decreases. As capacity decreases, number of people admitted to hospital decreases. And remember, I started this loop, talking through this loop, by saying the number of people admitted to hospital increases. So I've reached a contradictory conclusion. I've said the opposite after I've been around this loop, which means it's balanced itself out, and therefore is a balancing loop. So it's a good little test to sort of talk through out loud your loop to make sure that your loop makes sense in terms of balancing itself. Okay, let's think about another system. Let's consider a really simple system, that of the chicken and the egg. That is indeed a system. And it is a system because chickens lay eggs. Okay, eggs hatch into chickens. Hope you're with me so far. Now, more chickens mean more eggs laid. So the more chickens we've got, the more eggs we're going to have. Similarly, more eggs means more chickens hatching. So this is an example of a reinforcing loop where we've got chickens who are laying eggs, and the more chickens we've got, the more eggs they'll lay, which will hatch into more chickens, which will mean more eggs hatched, more chickens, etc., until we are overrun by chickens. That's a reinforcing loop. Okay. Right. So I want you to have a bit of a practice at building a causal loop diagram. What I want you to do in your groups is to try building a causal loop diagram that describes the causal influences for people adhering to social distancing and other preventative measures during the COVID-19 pandemic. What I want you to do, the way I want you to do this, is to start in the middle by writing a series of entries that cover different measures. Things like, I've given some examples here. So number of people wearing masks in required settings, number of people staying 2 meters away from individuals not from their household, number of people washing their hands regularly for at least 20 seconds. So all of those kinds of things that we're all very familiar with now, unfortunately. But those kinds of things, put them in the middle of your page. Once you've done that, I then want you to start thinking, first of all, about as many factors as you can that will directly influence each of these numbers. So what directly influences the number of people wearing masks in required settings? What directly influences the number of people washing their hands regularly for at least 20 seconds? And for each influence that you identify, you should indicate the direction of the influence and the polarity. So is it the case that as this influence goes up, that this thing goes up, or do they go in opposite directions? So you put a plus or a minus at the end of the arrow. Then once you've done that, so as you start to build this out, then think about if any of these factors that you've identified that influence these things here link up with any of the other factors that you've written. So does something that you've written over here that influences the number of people wearing masks, does that also influence one of these things over here that influences the number of people washing their hands? And if so, what's the direction and the polarity of that influence? And then start building out from that. So, okay, so I've identified something that directly influences the number of people wearing masks. What influences that? So looking for things that here that influence something that influences the number of people wearing masks. So you're gradually building out and thinking about the causal relationships for each of these things and doing the same. So each time you're going out, you're then thinking, do any of the things that I've written down link up to any of the other things I've written down directly? So you keep building up your map. And the key thing you need to be on the lookout for are these feedback loops, reinforcing loops, and balancing loops. Now, my advice, because these things can get quite big quite quickly and quite messy, I would be on the constant lookout for your reinforcing loops and your balancing loops as you go along. And when you think you found one, I would personally write that on a separate sheet, or on a separate digital sheet or digital page. Make a note of that loop and indicate whether it's a reinforcing loop or a balancing loop, so that you've got a note that loop is in there, because it's those loops that you're really looking for. You're looking for things where you've got a snowballing effect, which is either positive or negative, that's either a good thing or a bad thing, which is telling you about some dynamic in the system. And you'll have balancing loops, things that kind of balance themselves out, and those things tend to be things you don't need to worry about too much, generally speaking, unless you're looking for a general increase or decrease in your system. So generally speaking, the reinforcing loops are the things you want to be aware of, because it indicates a problem that's getting worse. But whereas the balancing loops tend to tell you, okay, but this is potentially a problem over here, but it balances itself out, so it's not necessarily part of the problem. So I want you to work in teams to do this, because you need to do this as a group activity. And I want you to think about building this map up and think about what insights you can draw. And that's really important. So think about not just building up the map itself and identifying the loops, but what does that mean? What insights would you draw from this map that you've built up? What's this map telling you about the system? There's no solution for this, because this is an exercise where you're just going to try building up this kind of map and see what emerges. Just to give you some practice on doing these causal loop diagrams. Now I'm going to give you till 11 o'clock, so you've got an hour to do that. Make sure you stretch your legs at some point towards the end of that as well. Work in your groups. I'll be dropping into the various sessions as well. So if you need any help, do shout. But just run with this. Have a think about your causal relationships, and remember to build things up gradually do it gradually, look for your loops, and also make sure that the influences you're identifying are direct influences. So what things directly influence the number of people wearing masks? Because if it's not a direct influence, that means it's in turn influencing something else, which influences the number of people wearing masks, and therefore you need an influence in between. Any questions about any of that? No? Good. Okay. Have fun. We will rejoin at 11, and I'm going to be asking a number of groups to present their maps this time and what insights they have drawn from this. So have fun. I'll be dropping into the sessions, and I'll see you at 11. Thanks, everyone.